Good morning, students. This is an opportunity to welcome you back to this semester. My name is Bamsheli Samson, and I'm the lead tutor for Csc204 Assembly Language. This particular course is going to be taken by 3 different lecturers, and we have at least divided into segments. So I'm starting the class with you guys, so please pay attention from the beginning to the end so that you won't miss anything at the end of the day. This section 1 course unit 1, as we have always been doing it. So then the objective of this particular course is straightforward. It is to help the student to understand, more fully appreciate the service provided by the runtime system associated with a modern high-level programming language as they acquire the ability to program in assembly language. Because most of you have been introduced to high-level language whereby you use your Python, Perl, and the rest of it. But there are assembly language that students must be able to program so that they can develop their own students. That is the reason, that is the basis for you to understand this particular course. The second objective is to facilitate the study of the architecture and organization of the computer upon which assembly language is executed. Then to also provide knowledge of assembly language to the students who already are programmers so that they can become more efficient in high-level language. Because once you understand the low-level language, which is assembly language, and you understand how it is being programmed by the programmers, it is even making more efficient when you are programming at the high-level language, using the high-level language. The assembly language assembly language programming develops a very basic and low-level understanding of computer. It aims at bypassing the intermediate distance between the computer and the high-level language programmer. The aim of programming in assembly language is to bypass these translators and compiler, impose intermediate, and communicate directly with the computer, since assembly language and its more primitive variants, machine language, has a structure that is directly compatible with the architecture of a specific computer. In effect, they are often small and very fast. You know, we've discussed this thing. Compiler, all these translator, compiler, interpreter, they are intermediate between the assembly language, between the assembly language, or between the computer itself and the programmer. Because in any language that you want to program, be Java, Python, or any other form of language that you want to program on, you need a compiler to do the interpretation for you. But programming in the assembly language makes you communicate directly with the system. It makes the programmer to communicate directly with the system without needing the help of compiler. That is why we told you in the previous class, in your 101 and 102, that no assembly language that can be moved from one system to another. That is, one assembly language is per system. It is not transferable. Do you understand what we are trying to say here? So many computational feats that are difficult or impossible at a high-level language can be accomplished in assembly language. With a good knowledge of assembly language, it is believed that a student can write better programs even when using high-level language. If you have the knowledge of assembly language, there's practically no program in the world that you cannot program with. Or you will even be more efficient when using other programming language at the high level. So the outcome that we expect at the end of this program from students is to acquaint the student with the knowledge and techniques of using assembly language by bypassing translator and compiler imposed intermediate, inherent, in high-level language programming and communicate directly with the computer. If you understand what we mean by that, the purpose and the aim of you going through this course is for the student to understand how they can bypass compiler and translators and communicate directly with the system, and to also explain all the basic operations of the computer and in essence understand the psychology of the computer. The purpose, so that if you understand how machine respond or how machine language or how machine works, this is an opportunity. With assembly language, you will be able to understand the psychology of a computer and to also recognize the von Neumann architecture as the fundamental concept of all stored program computer. That is, for all the computer that has capacity to store information, they follow the von Neumann architecture, and you need to understand the concept behind it. That's the purpose. That is what is expected at the end of this course. So, introduction. Von Neumann architecture. All the conventional modern computers are based upon the concept of store programs computer, which means the executable instruction and data are kept in the same memory. The credit for modern computer architecture goes to John von Neumann, this great mathematician, and the credit of modern computer because he is the one who developed the conventional model architecture for modern computers, and all the concept behind all modern computer that is based on stored program, it is done based on von Neumann architecture, which takes us to which you need to understand that, and all this process started from 1903 to 1957. See the architecture. See the simple architecture. This is. Are you there? See the von Neumann architecture. You can see that the input and output channel, if any, you can see it comes straight to the memory controller, and memory address register is in front of it. How he allocates all those space. The memory address, memory buffer register, then which comes to the main bus where you have your location counter. You have instruction register, you have instruction interpreter, then you have instructions, data working register, general register, and other CPU, if any. So this is simply von Neumann architecture, which you need to study the architecture and see how this is being designed and constructed. So the component of general machine structure. Hello, we have the instruction interpreter. Instruction interpreter, it is a hardware device which gets the meaning of the instruction fetch from memory. Instruction interpreter is a device which gets the meaning of instruction fetch from the memory. He is the one that knows the meaning of the instruction that is fetched from the memory. Then we have the program counter, also called location counter or instruction counter. It is the memory device which denotes the address of the current instruction being executed. He is the one who knows the locations, the address of the current instruction that is being executed. That is the program counter. Then we have instruction register. A copy of the current instructions is first brought into instruction register, which is used by instruction interpreter subsequently. So the copy of the current instruction will first of all brought to instruction register, just like to register that instruction, so that instruction interpreter can subsequently, do you understand, make use of it. So that takes us to working register, WR. They are memory devices used by the instruction interpreter. They serve as scratch pad for the instruction interpreter. Then we have general purpose register, GPR. They are used by the programmer for various arithmetic and logical operations, and also as base register to store address. They are used by programmer as storage location and for specific function. The function of me moving from my position to outside can easily be what? Stored in the in general purpose register. Most of the programmer use this for arithmetic and logical operations, and also as base register to store addresses. They also use this as a base register to store addresses. Then we have memory address register, MAR. Contain the address of the memory location that is to read from or to store from. Memory address register. Just make sure that you don't mix these definitions together. You have to understand the concept behind all these registers. That is inside machine structure, so that you will not mix them together. So the MAR contains a copy of the content of the memory location. You will take from the general purpose now. You will take a copy there. That is, this copy, whose address is stored in MAR. The address has been stored in the MAR. So the primary interface between the memory and the CPU is through this memory buffer register. It is from this the processor will fetch from here. The central processing unit will fetch from memory buffer register. Are you with me? So and RAM also will fetch from memory buffer register. So it is an interface between the CPU and your main memory, which is your RAM. Memory controller. It is a hardware device whose work is to transfer the content of the MBR, memory buffer register, to the core memory location whose address is stored in memory address register. Let me take that again. Memory controller is an hardware device whose work, that is, whose main job is to transfer the content of memory buffer register to the core memory location whose address is stored in memory address register. Then we have input and output channel, which was hello. So inputs and output channel may be thought of as separate computers which interpret special instruction for inputting and outputting information from the memory. If you might only, but they can also be peripheral, whereby they bring in input and output into the specific computer, which interprets specific instruction for input and outputting information from the memory. The basic operation or the basic computer architecture. The basic operation design of a computer system is called architecture. John von Neumann is a pioneer in computer design. Is given credit for architecture of most computers in use today. For example, the 8x86 family uses the von Neumann architecture. A typical von Neumann system has three major components: the central processing unit, the memory, and the inputs, the memory and input and output, or I/O. The way a system designer combines these components imparts system performance. That is, if you are designing a system from the beginning, programming a system from the beginning, the way you make use of these three components of von Neumann architecture determine the functionality of such system. In von Neumann architecture machine like 80x86 family, the CPU is where all the action takes place. Everything takes place from the central processing unit. All computation occur inside the CPU, data and CPU. Data and CPU instruction reside in the memory until required by the CPU. To the CPU, most input and output devices look like memory because the CPU cannot store data to an output device and read data from an input device. The major difference between the memory and the input and output location is the fact that input and output location are generally associated with external devices in outside world. Input and output location are always referred to as what? Associated with external device in outside world. And CPU does not recognize them. It only recognizes the memory because it does not have capability to store data. It fetches the data from the memory. So when an input and output instruction is coming, it sees it as memory because it's going to read it from there. Diagram of connections. So look at central processing unit here. Look at random access memory, RAM, which is your main memory. Look at the bus system, which carry all the signals to and fro. Then look at display device, which is output device that shows us what is inside the system, or show us what we use it to instruct the system. It displays all the activities of the system. Then we have the keyboard, which is an input device, so it's an external listening. Then there's a bus also which connects both the input and output device to the RAM. And when central processing is running, it's the bus that takes all those signals to and fro. Do you understand what we are trying to say there? I've mentioned it that a processor also has its own memory, like cache. It has its own buffer. It has where it can store information temporarily during operation. So, and what the register is trying to tell us is that when when you want to carry out two operand operations, when you place the first one on register, no, when you place the first one on register, you can actually fetch the second one from the memory and add those operation and place the result of those operations into another memory cell. But they also tell us that CPU also has a memory because it is more faster when we bring the two operand into a processor, because what we are capable of doing inside a processor is fast, it is more efficient than having to go outside the processor to fetch for other data like other operand. That is, if one is stored in the register, we can actually bring the other one on the and processor has capacity to remember where it stored information inside it, and then process those information and store it in another cell. So this is what CPU register is being used for. So that takes us to conclusion of this exercise. In this unit, you have been able to learn the concept of von Neumann model architecture, which deal with computation concept of all stored program in computer machine. You have been able to at least understand the architecture of von Neumann. So that's what. Then the summary. We said the primary function of computer system is to do what? Is to process the input data to yield a result that can be useful in a specific environment or specific application. Then we also went through von Neumann computational architecture. Then we also told you that it consists of 4 basic units: memory unit, arithmetic and logic unit, control unit, and input and output unit. These are 4 key units that is inside the von Neumann architecture. Finally, you have also seen that the major hardware component of most computers available in the market today are interconnected according to the von Neumann model, and therefore described as von Neumann computer. Thank you for listening.